Systems at equilibrium are sometimes subjected to what we call stresses, and in life, so are we. So this is a good application of how we adjust to stress to kind of reduce that stress. Same with chemical equilibriums. That's the primary focus of this podcast. We'll take both a qualitative as well as a quantitative look at the various, quote, stresses that a system at equilibrium can experience. You just completed a lab that helped you to examine various systems at equilibrium, and you were asked to change the concentration, the temperature, or the pressure of these different systems. The catalyst, I'm not sure that the lab addressed that, but that's the purpose of this podcast, is to kind of review what you learned in lab and discuss how a system will overcome a stress that is added. For example, if you increase the concentration of either a reactant or product, or change the volume of a system at equilibrium, change the temperature. Notice that there's only one time where the stress that's added to a system at equilibrium will cause a change in the value of K, and that is when temperature is changed. K is always temperature dependent, and so a change in temperature changes the numerical value of K. In the previous podcast that you listened to, you did some calculations while learning equilibrium calculations, and I'm going to go back to these problems that you looked at earlier and take a look at the values that you calculated for concentrations and look at what happened to the system. This system at equilibrium was studied and calculated earlier, and what you calculated is that when acetic acid, which of course we know is a weak acid, is placed in a container with 1.0 molar solution, we can end up with a solution that has a pH of 2.37. Actually, where we're going in the next chapter, acids and base equilibrium, we will be able to tell by measuring the pH of an acid of known concentration, we can calculate the K value. That is one of the goals of one of the acid-base labs. Given the concentration of the acid and the pH of the solution, calculate the numerical value of K, which is shown here. But you'll get to that soon. Just a little bit of a backtrack a bit to ask the question, what is the percent dissociation? Since it's a weak acid, we know that only a small percentage of the acid dissociates. If we calculated the concentration of the hydrogen ions, which also is in direct relation to the concentration of acetic acid that dissociated, we can calculate the percent simply by putting the part over the whole times 100. So we can see that in this case, did I do my math correct? I think so. 0.24% of the acid dissociates when no ions of hydrogen or acetate ion are added to the system at equilibrium. You did a calculation from the previous podcast, so call up your answers to this question where you're asked to solve the pH. When you went and calculated the pH, I assume that you found that the pH indicated that the solution was less acidic or the pH was higher. So what does the addition of sodium acetate do to the amount of acid that dissociates? Well, actually what it does is it decreases the percent dissociated. Calculate that value and bring it into class next time we meet, the percent dissociated. But you can see that your value of X that you calculated, okay, once you figured that out, that less hydrogen ions were formed because of the presence of the acetate ion. So the increase in the acetate ion caused the equilibrium to not proceed as far forward as if there were no acetate ions present. In each of these slides, we see examples of ways in which an equilibrium can be shifted by changing adding reactants or products, changing the temperature, or actually changing the pH. All of these are similar to what you experienced in lab. I think the first one is an equilibrium that you studied in this lab, although you may not write the reaction the same way because there's other things involved, complex ions. This is an oversimplified version that I show first-year chemistry. However, if you heat up, if this were solid, you're dealing with aqueous solution. So if you heated up solid cobalt chloride hexahydrate, the water is driven off and you have a color change, adding energy in the form of a raised temperature. The system will react to try to compensate for that added energy. Notice the wording there. The system will compensate to use up that added energy caused by an increase in temperature. To use up the added energy, in this case, the forward reaction will occur to a greater degree. If we go back to kinetics, that means that more molecules will have enough energy to cross the high activation energy and produce more products. So in that case, K, the numerical value of K will change, and the ratio of products over reactants will change as well, increasing more products, decreasing the amount of reactants, and thus in this case, K will increase. Again, both of these two reactions, solubility of lead chloride and the flower power demo, the forward reaction is endothermic. When the forward reaction is endothermic, again, adding heat in the form of changing the temperature, the system will adjust by trying to use up some of that added energy. In this case, since the forward reaction is endothermic, the forward reaction will occur producing, to a greater degree, producing more products than reactants, thus raising the numerical value of K. If the energy term were on the product side, then raising the temperature would have the opposite effect. And finally, introducing pH a few times in this unit, getting ready for our acid-base chapter. Raising the pH means you're lowering the concentration of the hydrogen ion. So if you lower the concentration of the hydrogen ion, the system is no longer at equilibrium, and meaning the reactants are too low in concentration, and so the quotient Q is too large. So in order to reduce that value, the reverse reaction would have to occur, producing more reactants, making the denominator larger, and returning K to the original numerical value. K remains unchanged when you change the pH, when you change the concentration. Your lab looked at this equilibrium system as an initial inquiry, and you change the concentrations of either the reactants or products in various ways. But my question to you to consider and to pause this podcast for a moment is to think about a mathematical approach to what impact will adding water have on this system at equilibrium. It turns out it does depend on the equilibrium system, depending on how many reactants and products you have that are dissolved in water. In this case, we have one product and two reactants, coefficients all being 1. So take a moment and pause this podcast and to take a mathematical approach to this. And by that I mean, instead of writing this in brackets as concentration of FeSCN, write it as moles of iron thiocyanate per liter, and same for the iron and the thiocyanate ion. And see if you can predict which way the equilibrium will shift. I'm not talking about a change in the color just to lighten it by dilution. I'm talking about an actual shifting of the system at equilibrium. All right, so to go through it. If you look at this relationship here, K is a constant. So we have one unit of liter in the numerator, actually it's in the denominator, and 2 units of liters in the denominator. So if liter goes from 1 to 2, what does that do to the numerical value of Q? So diluting brings about a Q that is larger than K. Since K and Q are products over reactants, in order to reduce the value of Q to the equilibrium constant, you'd need to produce more reactants, fewer products. So the reverse reaction occurs when dilution occurs in this system. Okay, let's take a new system at equilibrium, shown in blue. And as you can see by the 197 kilojoules on the reactant side, again, we have an endothermic forward reaction. So can you, based on what you've learned so far in this podcast and your reading, can you explain why, when you increase the temperature, the numerical value of K will increase? As the temperature increases, the system will adjust to compensate for that increase in temperature by allowing the forward reaction to occur at greater frequency than the reverse reaction. So more products are produced, fewer reactants are present when the system readjusts. So now the ratio of products over reactants is a larger value, and thus the value of K, products over reactants, has increased. Next question here, can you predict what will happen to the partial pressure of SO3, which is a reactant, when the system is compressed? You've got it. As you lower the volume by compressing the container, the system suddenly has an increase in pressure because of this decrease in volume. And in that case, the pressure is going to try to compensate by reducing the total pressure. And the way to do that in this system is by the reverse reaction occurring, producing more SO3 and fewer molecules of SO2 and oxygen, returning the system to equilibrium. Does compressing the system alter the numerical value of K? And the answer is no. Decreasing the volume increases the pressure. It also, decreasing the volume, increases the concentration. But then once equilibrium is reestablished, the numerical value of K will also go back to, or will remain the same, remain unchanged. Here's an example of a heterogeneous equilibrium where you have gaseous products and solid reactants at equilibrium. Should be a double arrow here. And the question is, there are multiple questions. So if we have Kp, we know that Kp is 1.0, and since we're talking about Kp, then we know we must include units for K. The only time we do include units for K is for Kp, since it depends on whether it's in millimeters of mercury or atmospheres. So in this problem, you're asked to calculate the partial pressure of HCl at equilibrium. And since we have a system at equilibrium, it's safe to assume, it's accurate to assume, that some of all of the reactants and products must be in the system at equilibrium. So stop for a moment and try to calculate that value. And then when you're finished, read on and try to see if you can just do this on paper. Calculate the second and the third problem. In this second problem, we're shifting the equilibrium, and you're asked to qualitatively describe how this amount of solid will change. Will it increase or decrease or remain the same when you add some HCl to this system at equilibrium? And then in the second part of that problem, you're asked to calculate the pressure of HCl that is reached at equilibrium. And then finally, if you go to having this system's volume increase, going from 1 liter to 2 liter, what will happen to the pressure of HCl at equilibrium when the volume is increased? So pause the podcast, take 5 minutes or 10 minutes, whatever it takes, to perform the calculation before moving on, because the next slide shows the answers. You want to check to make sure you can do this by yourself. All right, so did you arrive at 1 atmosphere? Pressure of hydrogen times pressure of ammonia has to equal 1 atmosphere. So since they're equal to each other because of the mole ratios in the balanced equation, then the partial pressure due to hydrogen, or excuse me, due to HCl would be 1 atmosphere. What would be the total pressure? The total pressure would be 2 atms, if you think about it that way. Pressure of hydrogen, HCl, plus ammonia. All right, so after HCl is added to the system, quantitatively, I think you can read through the explanation, you've caused the system to be out of whack, so the added HCl will tend to be used up, using up some of the ammonia, and so both of these things will combine to form more solid. But in the end, when the equilibrium is reestablished, in the end, you'll have more HCl than you did initially, greater than 1 atm pressure, and less ammonia than you had initially, so that the numerical value of K still remains at 1.0 atm. And in the calculation, which I didn't bother to calculate, I'll have you bring in those values. This would be the mathematical approach that you would use. If you had added, as I recall, 0.5 moles to a 1 liter container, that would be 0.5 molar. And if we assume there's no volume changes, essentially, because volumes of gases are independent of one another, then the system would be set up in this way. Calculating X definitely would involve a calculator. Bring that value into class tomorrow. And then finally, I think this is a bit tricky when you think about it, but remember that concentration and pressure are two different things. And so how the system will equilibrate, you might say, well, raising the volume would cause the system to shift to more products. Well, initially, yes. But if you think about it, maybe not. If you raise the volume, all of a sudden the pressure has dropped for this system. The pressure of ammonia has dropped, the pressure of HCl has dropped. And because these two pressures have dropped, the numerical value of Q is less than K at this point. So the pressures of each of these gases would need to increase, and that would occur by more of the ammonium chloride decomposing to form more gases. But once the pressure returns to the original equilibrium partial pressure, the system has now reestablished equilibrium. So actually, in this case, the pressure of ammonia and HCl remains the same. Sort of reminds me of vapor pressure calculations in a way, if you think about it. So you have one final calculation to perform. So one final calculation to perform. Bring the values that you do calculate to class tomorrow. Starting with 1 mole of NOBr in a 1 liter container, and knowing that 34% of that molecule decomposes at equilibrium, can you calculate both Kc and Kp in whatever order you wish? Knowing that the volume is 1 liter, the temperature is 25 degrees Celsius, you should be able to calculate not only the total pressure at the start, but the total pressure at equilibrium as well. So calculate Kp, Kc, and the total equilibrium pressures. I'll just give you a sneak peek as to some of the ways to begin this. If you think about it, the pressure and the number of moles are related. Remember how Kp and Kc are related? And know that the total moles is related to the total pressure. So these hints should help you get started. Good luck. Have a good night.